Hey, we have this habit of always, when we have awesome speakers like we have today, several of them, welcoming them all with a big applause. Are you all ready? Now it's time. Let's do the big applause. So happy to have Will and Dario here from Cisco's team. I heard stories about what they're going to say. I haven't seen the main thing. Then I had the chance to sit a couple of long evenings with Will and thinking about where the world might be going with all this. I was happy to invite the crew in here, and the floor is yours. For the practicality's sake, for the reason what we have on the demo, Will and Darius at least wanted to start without the mic. Are you also brave there in the back row as well, that you're brave enough to raise your hand if you don't hear? Yes. You're all brave people over there? We trust on you.
Yeah. See, this may be a good time to come forward if you want. Can you hear me back there now? Okay, great.
Good, brave people.
Test 1, 2, 3. Okay.
Okay, so just a little bit about Dario and I. We work on a research team within Cisco that looks into machine learning and AI. We're part of the larger team that's building sort of Cisco's Alexa. So it's an AI system that you can talk to. It's got cameras and speakers and the big screen and everything. And so we have access to all of these good cameras and mics and screens. And so we were trying to take advantage of all of that and build an AI that's kind of an end-to-end AI that can interact with people, not just over voice, but using subtle gestures and your gaze and various things like that. So I guess how this relates to what Tempo and Digitalist are doing is that we're thinking deeply about how humans interact with each other, how they learn from each other, and we're trying to teach an AI to do that. So to pay attention to the things we pay attention to and learn how we learn.
Yeah, we can start. So as Will mentioned, we want to learn from humans how humans interact. And so there is some study behind that we did, and we took inspiration from the way our brains evolved. And we see that actually there's sort of two brains that evolved during the years. And in mammals, especially, we have two parts. The old brain that learn to encode inputs in a very specialized way. Ears and eyes can encode the inputs in a very specialized way. They evolve through years. And it's the new part of the brain, the neocortex, as it's called, and it's more generic. And we see that the smarter the animal is, the smarter the mammal is, the bigger this part of the brain is. And we got inspiration from this to build our own machine, our own AI that we want to show you.
Yeah, this is one of the big reasons why humans have advanced so far so fast, is that unlike most other animals in the animal kingdom that just have these specialized parts of the brain to do specific things, we have this neocortex that can learn new tasks given any kind of input. So it's sort of like a general algorithm that can process any input, and recognize patterns and see anomalies and things like that. So if you, there have been experiments done where the picture there of the blind woman with the sensor in her tongue, she's receiving visual input on her tongue through these little sensors, and they're little sort of pricks of electricity. And it's basically giving her an encoded version of what the camera is seeing that's on her glasses. And her brain has learned to turn those encoded patterns into vision. And so when she's walking around, she doesn't any longer feel the sensations in her tongue, she sees. And if they look at the brain, it's lighting up the same parts of the brain that light up when we see. And so the brain has repurposed itself to process information in a new way, so that the touch part of the brain is processing vision. And that's possible because of the neocortex's general algorithm.
It's a very flexible algorithm, and there's an experiment I wanted to mention. Two experiments. One that we didn't do, where they wired the neurons from the eyes of a mouse to the part of the brain that used to hear, and vice versa, the part of the ears connecting them to the part of the brain that would see. And eventually the mouse learned again to see through the ears and vice versa, because these neocortex is very flexible. That experiment we did, we bought this active vest, like a vest with multiple buzzing devices, and we tried to encode sounds and names, and eventually we learned to feel that, we encoded wheels. When Will was sending me messages, I wouldn't see Will messaging, but I would feel that Will sent me a message, and my brain eventually just stopped recognizing patterns consciously but subconsciously. It was a very interesting experiment.
Right. So anyway, this is all prefaced. This is kind of how we're thinking when we built this AI. Now, the main way that we did this was we thought of the neocortex in our program as kind of like a loop. And at every sort of tick in time, so every moment in time, it's reassessing what it knows. And so the time step goes by, and it's receiving information from its senses. So we built separate implementations of senses. So we have something that can see, hear, recognize faces, detect gazes, see objects, various things like that. They're all running in their own internal loops, and they are telling the central neocortex what they know. And at every time step, the neocortex is thinking, okay, what do I know now? I know I see a couple of faces, I hear a voice, I see an object, what do I make of all that? And so we try to create a meta-learning layer that takes all that input from those lower-level AI tasks and does higher-level reasoning. So we're going to try to show some of that tonight. And just as a caveat, normally these things run on big GPU machines, and we've got an array of them. We're running it all on a laptop with just a CPU. So we've had to squeeze all of our models down, and they're not quite as accurate, but you'll get the idea.
Yes. So the first, we wanted to build senses from the ground up, from very simple ones to more complex ones. And we want to be inspired by humans. And what babies can do very easily is to recognize when someone is talking. It's binary. Is someone talking or not? So we wanted to start from something very, very simple. And you can show. Okay. We will see that we are growing with AI. We start from what infants can do, and then probably from toddlers, and then from 4-year-olds, and so we build more and more advanced skills and combine them together. So what you can see here is that this red dot is the feedback for us to understand what's going on. If I shut up, it disappears, and if I talk, it goes back. So it knows that I'm talking. That's the very first interaction we can have with babies and with our baby AI.
Right. So this is just the first little sense, and this is just, is someone talking? That's all it's trying to figure out. But you can imagine if you're trying to teach an AI something, it knowing that someone's telling me something is the first step. Okay. The next thing we'll show is gaze detection. So, when you're interacting with, say, a child and you're trying to teach them something, I've got a couple of kids, you look at them and they look at you, and it's a signal that something is about to be transmitted, right? I'm going to tell you something, give you some kind of direction. So we trained a model that can basically detect your gaze and tell where you're looking. And this is another sense that we're inputting into the neocortex. Let me run that. Okay, so this is trying to figure out if I'm looking at the camera. So right now I'm looking right at the camera, and you can see it's right, and I can turn my head left and right. It's detecting kind of where I'm looking. If it turns red, it means it thinks I'm not looking at it. That's what it's trying to do. If Dario comes to the picture, it'll find his gaze too.
And look at the camera. It turns green.
Right. So anyway, it's trying to make a prediction about whether or not you're engaged with it. And it's using, basically, you can see the little pose points on the face, and it's using those, and it's passing those into a neural network that predicts the angle of gaze and such, the yaw, and all that sort of thing from that input. Okay, so now we've got an AI that can knows you're talking to it, and knows you're looking at it.
So as we are growing, I guess, after we see when people are talking to us, we can see when we can hear and we can see that. Next is making sure that we know we are object permanence, right? So we want to make sure that an object through time is the same object. I can see Will's face, and even if it moves around, it remains Will's face. That's what also toddlers learn more or less when they're 4 years old. You can show something and then you hide it, and you show it back, they know it's the same. Before that, they can't. So we wanted to do something similar to that. And this is important for any sort of tracking what's going on. You want to remember what's happening in the last seconds. You want to make sure that the same object is remain the same. And so we can show you with faces, for example.
Right. This is something that's trivial for humans to do. If I hold up this microphone, it's just effortless for you to know that it's the same microphone, from there to here. But machines aren't like that. So for them, this is an object, this is a new object, this is something new, this is something new. And even if you have like the cat classifier from the last talk, microphone classifier, at every frame, a new classification step typically is made. And so tying all that together is not something that you get for free. So you have to teach these algorithms how to do that. So you saw a little bit of this earlier, but we can track any object, but I'll add faces for now, and we'll try another one in a second. So a couple things to note. One is that it knows it sees a face, but it knows it's the same face as previous time steps. So that's why it's the same color. And if I move around, I can't really lose it. And if I go away and I come back, it finds me again. So the objective here is for it to know it's the same object through time. If Dario comes in here, it sees him too.
And if it disappears again, it knows it's the same face from before.
Right. And so the way that works is that when it detects a face, it basically uses one of these encoding techniques, uses a neural network to essentially turn the face into a kind of set of numbers in space. And those numbers are semantically meaningful. So a face that occurs here in that space and one that occurs here are similar, and one that's way over here is not similar. And so we trained it on millions of faces. It learns how to encode any face, and so when it sees a new one, it's able to represent it in a way that it can track. So when it looks at future frames, it says, okay, I see another face. It is very similar, based on that encoding, to the one I saw before, and it makes an assessment if it's the same one or not.
Yes. So this sort of encoding we are learning is what evolution did for us. We had to millions of years to evolve to be able to compress information in a meaningful way, and we can do with faces. And the next thing, we can also track different objects like people. For example, if I turn around, my face is not visible anymore, but we're tracking people. Step out.
Yeah, so now it knows I'm a person, and people do things like turn around, right? And even though it doesn't see a face anymore, it still knows I'm a person, and it knows I'm the same person. And if Dario comes in, it knows he's a different person still. And so, a lot of people working on face detection and recognition, and what happens typically is the second someone starts to get obfuscated or obscured from the camera, it doesn't know who they are anymore. So we've done things where we've combined face and voice and person detection to basically create continuous recognition so you can't be lost. Okay.
So now we've done a lot with video. The next is a very simple task with voice. We want to do something a bit more complex. As a human, it's pretty trivial for me to recognize voices.
Fire for you.
Faces, right? So it's difficult when it's on the computer. What I want to show is what happens if we are able to do the same trick that we do for faces for voice. So here you can see two things. You can see my face is being seen and the audio. And these blue dots are a representation of my voice fingerprint, as it was we can say. So computers transform our voice in numbers, and as we'll explain, my voice should be represented with numbers that are close to each other. And you can see there are all dots, and especially one person. So they're just being placed there. It doesn't know what to do with it. It's just placing them and memorizing them. And if we start talking now.
Right, so if I join the conversation, it's going to think that it's detecting a new voice. It's going to try and cluster my voice separately from his voice. Now, it's never heard either of our voices. Every time we start this loop up, it's like it was just born. It knows about voices, but not about us. And so in real time, you can see beginning to separate the voices as best it can into two clusters. And so what that lets you do is like real-time speaker identification. So you can see now the clusters are fairly well identified, and it's learned two new voices, just us talking here. And in a few, I think maybe a couple slides, we're going to show how we can tell it now who those clusters belong to, and so you can have basically auto-enrollment to if you're doing speaker or face recognition.
Yeah, that's more or less what we're doing. Even if I don't know your name, I can start recognizing your voice. You have just person one for now, and you tell me your name, I know your name and associate with your voice.
Right.
This is pure unsupervised. This is just based on these senses that we build instead of through evolution, through training on not on my voice, on thousands of other people's voices. You never heard my voice before. Every time you start this machine, this AI, it starts from scratch. It learns as we started 1 minute ago.
Right. So the next thing is gestures. So another way that humans interact with other humans is through gestures. So I might wave at you to get your attention. I might say good job, okay, come here, right? Get the microphone. So these are kind of built into the way we interact with people. Maybe something fun. And so we wanted to teach the computer to do this as well, right? So I'll show you a video of that. That's the easiest way to do it. And this is just a set of, we taught it how to recognize things like waving and swiping and such. And the thing you see on the bottom right, what we did there is that our AI loop has a memory. And so what it's doing is that over time it's detecting motion. And then what it does is it squeezes all of those motion frames together into a single frame. And so what you're seeing there, when you see the kind of dragging effect, are past frames that have been layered on top of each other. And the advantage of doing that is it's an incredibly efficient way to give a machine learning algorithm data, because we've compressed 10 seconds or 3 seconds or whatever into a single frame. And it's able to then, you can even see yourselves what the motion looks like. So when I was raising my hand, you can see, even visually as a human, what's going on there. And so we taught it gestures. And to teach it new gestures, all we do is we say, okay, I'm going to teach you a gesture like, okay. And we just do it a lot, right? And it can learn it in about 50 examples with the algorithm we built, which is incredibly small data for these kinds of problems. And it's because of the input we're giving it, that motion-infused frame.
Yeah, so as you mentioned, each of these senses, it's like part of a small brain, and it has its own memory. And it can be memory through time or through space. It doesn't really matter, as long as there is communication with the neocortex happens in a meaningful way. This encoding is fast and it's created so that they all process in the same way. It doesn't matter what the part of the brain for gestures is doing, as long as the information is created. There is memory through time. For face, it is memory through space and time. So that's the power of dividing the tasks to dedicated small brains.
Okay. The next thing we're going to show is we're going to try and put things together now, or begin to put them together. So we're going to use the gaze detection, basically act like a wake word. So if you've ever used Alexa or Google or whatever, you have to say this wake word and they wake up and you say something else. It would be much nicer if you could just look at it and talk with it, right? So that's what we're going to show, is basically a gaze-based ASR, wake word. Let's see.
Show the volume.
Yeah, I think this is. Okay, so what I'm going to tell this thing to do is run, do face detection, do gaze detection, and when I look at it, wake up and transcribe what I say and say it back to me. And so it's like when you look at a kid, you're trying to teach it a word, and you're like, table, table, and it goes table. So that's what you're going to see here. Hopefully. Okay, so I need the speech service. So. Hello.
Hello.
Okay, now I'm ignoring it, and I don't want it to do anything. I want it to just ignore me. So I'm doing something, I'm talking to my microphone here, as you do. And I come back. Hi,
Hi.
how are you? How are you?
How are you?
Cool. Cool.
Cool.
Right. So like I said, we're running these very lightweight models, so not quite as accurate, but that you get the idea, right? So we're beginning to see how you can layer on lots of these effects to get something that looks a little more intelligent than we currently see in say your average device these days. Okay. Let's see.
Yes.
So we're just going to say a little bit about how we actually do this for just a second.
Just 1 minute of curiosity. So we're talking about AI, machine learning, deep learning, and the hot topics is artificial neural networks. So that's what we're using mainly for most of our senses. That's how we train. We use artificial neural networks. And without going into details, we can see them as usual as a magic black box that takes an input and spits out an output. And what it is just a bunch of numbers. And we want these numbers to represent something meaningful for the machine and for us. So as Will and I mentioned before, these numbers should be so that if two inputs are similar, those numbers are presented in a closed body space. And if those inputs are different, it should be very different numbers. So if I put multiple images on my face, I will get multiple vector sequence of numbers that are similar to each other, and vice versa. If I get also a picture from Will, then those will be very different numbers. And the way we do it is a very interesting, simple idea, but very powerful. It's called this triplet loss training. Nothing fancy, but we start by training this magic black box by providing three inputs. For example, two inputs from my voice, me saying something and something else, and one from Will's voice. And we say, make sure that the distance that you output from this sequence of numbers are going to be close by as if the two inputs are from my voice, from myself. And they should be far away if instead I have my voice and Will's voice. And we did many times for hundreds or thousands of different people's voices or faces or any gestures, so we can encode anything, and eventually we can reuse it the way you saw it. We do with training on thousands of images or sounds what evolution did through millions of years.
Yeah, in some ways this is actually more efficient than the brain. The brain has to have specific encoders for every kind of sense. And with this architecture, you can train on any kind of data with the same architecture and get a semantically meaningful encoding. So it's sort of like it's a way of describing what it's seeing or hearing in a way that makes similar things feel similar to it, right? So if you have, say, a bunch of faces, let's say on a table you've got a bunch of pictures. And the kind of effect of this is when you start training, it's randomly distributed all the pictures. As you're training, you take a picture of someone, and you take another picture which you know is maybe of them or a family member maybe, and you're trying to push those pictures closer together. And if you take a picture of someone else, and you're trying to push that one further away. And so by the time the algorithm is run, you end up with a table where people that look like each other tend to be clustered together and it's sort of semantically organized. And you can do that with any kind of data.
And it works with new kind of data. All the face recognition and speaker recognition we saw so far wasn't trained on our voices or faces, but on other people's faces and voices, and it still works for newly distinct people. That's the power of these algorithms.
Okay.
I think we have time to show.
I'm going to do one more demo, which is kind of preposterous. We're going to try to run everything at the same time on this laptop. So if it blows up, hi. Let's see. So maybe that. To run sort of the main loop, the neocortex. Start up the voice activity detector. We need to run speaker. This one last. We need to run the speech recognition service, the one that talks, and then finally the gesture detection. So now we've run basically speaker. What's the service? Okay. Should I do this one? Okay, so what's going to happen here, it's going to be a little bit hard to explain, but what we think is going to happen is that it's listening to me right now, and it's beginning to collect information about my voice. And you can see the kind of numbers flying by. It's sort of creating those encodings of my voice. And it's learning about how I talk. So right now it knows there's a person there, it knows someone's talking, and it has a voice. And I'm going to try to tell it to assign it to me. Okay, that's right. My name is Will.
Hi, Will. It's nice to meet you.
Okay, now you can see that it's assigned Will to my face, and now when I talk, the little red dot is appearing on my face. So it's learned my face and my voice, and sometimes it gets it wrong. And then it's learned to assign it to me, and it's learned to put it when I'm talking on my face. Okay.
So if I start talking now, you should recognize that it's an unknown voice because again, we start everything from scratch. If I show my face, I'm a new face, unseen from before, and everything is new for him. And as it did for Will before, it's just collecting its face vectors and voice vectors. Sometimes it makes it does it wrong. It's fine. It's been alive for 1 minute, so we give it some slack. And so it's collecting more information as it can. I can do the same as Will did and introduce myself. My name is Dario.
Hi, Dario. It's nice to meet you.
So now it knows my face, it puts my name on top, and if I start talking, eventually it's going to learn better and better my voice, it's going to end up on my face, and it still gets it wrong, but again, give it some slack, and it's going to, the more we interact with it, the more it's going to learn to associate the right voice with the right face. And if this goes back.
Yeah, if I start talking again, it should eventually hear enough of my voice and start putting a dot on my face when I talk. All right, so it's it's learned 2 new faces, 2 new voices, and assign them, while we're sitting here. Okay.
I think we need to give a little more.
That's it.
Yeah.
Hey, perfect. Thank you. Thank you. That was pretty exciting. I think it brings a lot of questions in the mind. We definitely have time to take a couple of them from the audience if you have something in your mind, and then we're going to have a little break and head up with a little bit of group work after that. But questions?
Do you use 3D modeling, 3D model reconstruction of your face or facial recognition?
No, it's just trying on the 2D image. We do, for the gaze detection, does use the landmarks, yes.
Yeah.
Couldn't get out of my mouth. So we do have a model that learns those landmark positions, but it's using 2D.
Thank you.
Mary from here? Yeah. No.
Yeah, were you designing for specific business use cases or use case designed for these specific algorithms? Or was it more, let's see what we can do and then figure out how to apply them?
So, sort of both.
Yeah.
I mean, we're kind of research nerds, so we just want to see what it can do. Our bosses tell us it has to do something eventually, so we do try to make them happy. No, we want to take advantage of the hardware that's in the devices that we have. So I can't really tell you exactly what we're doing, but yes, the stuff you're seeing here will be appearing on these devices. Yes. Sorry.
No. Yeah.
So, is there a reason that you're using triplet cross instead of autoencoders and then performing clustering?
Yes and no. We use what works best, right? And triple loss seem to be pretty powerful. If you know FaceNet from Google, they use triple loss and it seems to be powerful. There are also many works using autoencoders. but you're not sure that the encoded vector is going to be useful for these kind of tasks you want to do. You can build on top of those, right? You can build an extra classifier or something on top of those. But for pure clustering, triple loss seems to be doing a really good job. Sorry, I've seen jobs works on autoencoders with triple loss together. We train together. So no real reason. We just choose what works best.
Awesome. Yeah.
I was just wondering how you pre-train your models where the data is from, and yeah, and then how you custom.
So yeah, you can gestures here, the expert.
Yeah, I mean, it depends obviously on the model. So for like the gesture recognition, that is we wanted that to be trainable on a small data set, so we actually created all the training data. And because of the input type, it doesn't translate full color images, just training on these kind of motions, and those are fairly generic. So even with small amounts of data, it's able to learn gestures. For other
the faces we started with experimenting with open source datasets, but then we have something internal. We collected it internal in Cisco, and for voice we're using as well open source datasets for now for showcasing and proof of concept. But eventually you start collecting within the company. That's less generic. That's more complex than the gestures because we need to have the full raw data. So we need more of those.
Are you putting aside golden sets to evaluate the models?
Say it again, sorry.
Are you putting aside golden data sets to evaluate?
Sure. Yeah.
Yeah, I mean, it also depends on the task. If you want to deploy it for certain customers, then we have the data from, we do meetings, so meeting rooms, and so on. So, yeah.
All right. Awesome. Hey, let's give a big hand for